Segura Lab uses is called a MAP scaffold. MAP scaffolds are granular materials made up of small, spherical hydrogel building blocks. What's neat about this material platform is that you can mix together building blocks of different compositions to make up your scaffold. That's exactly what we're doing to optimize vessel formation for tissue engineering applications. And right now, we're using our material in mouse models to see how vessels in wounded tissues and tumor tissues respond.
We've also developed clustered proteins onto our Hepar nanoparticles. For instance, we clustered VEGF, or vascular endothelial growth factors, onto these Hepar nanoparticles. And one application of this is to combine it with our MAP scaffold technology for a different application. One such application is injected into the brain after a ischemic stroke to get better recovery. By combining both our clustered VEGF nanoparticles and our MAP scaffold, we're hoping to get the best of both worlds and see better brain healing, both at the brain tissue level as well as functional motor recovery.
Have you ever wondered how you could use hydrogels to deliver genes locally to cells? You know, you can do a lot with flip scaffolds. You can use them for delivering genes to produce different biologics with manufacturing, or inject it as a therapeutic and help repair tissue. Wow, that research sounds so exciting. How can I learn more? There's been a lot of work going into FLIP to make it compatible with many tissues, from subcutaneous, intracranial, and dermal. While we have done work looking at ischemic stroke and using our scaffold to deliver things like viruses to help repair the tissue, our big claim to fame is working in chronic diabetic wounds, where we can deliver DNA nanoparticles to encode for things like VEGF to promote new vasculature, or things like IL-4 to help reduce the inflammation.
My project focuses on a specific, naturally occurring protein complex called heavy chain HA, where heavy chain comes from the serum protein called inter-alpha inhibitor, and HA stands for hyaluronic acid, of course. But why is this complex special? Besides being the only known covalent modification of HA, it affects innate immune cells to mitigate their inflammatory abilities. For example, macrophages polarize to more regenerative phenotypes, and neutrophils become quiescent. While I had originally designed an elegant protein fusion that uses the peptide ligating ability of sortase, I have since had to adapt to the less specific chemical modification using tyrosine NHS to make my heavy chain HA. Heavy chain HA can take many forms. It could be a viscous salve, it could be an externally decorated granular hydrogel such as MAP or FLIP. But in the end, the goal of heavy chain HA is to have it applied to a non-healing wound or ulcer, and have heavy chain HA reduce the local inflammation enough to permit natural wound healing.
Who's ready to do some science today?